Willwacher, and he will talk about deformation of EN operads.
Okay. So first of all, thanks a lot for the opportunity to speak here, and a special thanks for organizing a soccer match. So I think it's the first conference ever I've been to that ends in a soccer match. So I took the liberty to change the topic of my talk and not speak about recent work in progress with Carlo Rossi as I had originally intended to. So for those of you who wanted to learn about the other story, I can offer to give a private talk afterwards, so private discussion. Or maybe if I finish early, I have some words. I've never finished early, so so the new title will be Deformations of the EN operad. So the guiding question here is, we have the EN operad, by which I mean not the topological, but the vector space EN operad, so chains on the topological operad. And we know that at least over field of characteristic 0, let's say over Q, it is quasi-isomorphic to its cohomology, which I denote by little en. I think yesterday it was denoted by Pn, if I understood the notation correctly. And for example, one can ask, is there essentially unique quasi-isomorphism up to homotopy, or do I have multiple? And is it obstructed, or is the process of finding such a morphism obstructed or not? Can I do it order by order? For example, I was asked by Vladimir Hinic, and he had the impression that there's essentially unique such thing. Is that true or not? Now, in order to study that, what we have to consider is a version of the deformation complex of this EN operad. I will talk about this later. So the version I will actually use is the simplest version I can build combinatorially. So it's the version I would use if I would put it on a computer. You take a minimal resolution of this EN operad and you compute the derivations of this. And then the question is, well, what is this cohomology? So for example, the zeros cohomology here will parameterize infinitesimal choices that we have in writing down such a morphism. And also, if you have any EN algebra, and there are lots, then the zeros cohomology here will act on the algebra structure. So you can use it to change the algebra structure universally whenever you see an algebra over this sky. And well, we have to compute this. And the theorem I want to talk about is the computation of this guy. So maybe one word I have to say. So this looks very exotic if you're not used to it, but in effect, you see, this is a complex that has a certain bigrading. In each bi-degree, we have to solve some finite dimensional linear equation. The result will be a finite dimensional solution vector space, and it's completely classified by its dimension. So in effect, what we want to compute is actually not a higher structure, but a lower structure, namely just a series of numbers. And what are these numbers? And unfortunately, I cannot give you a completely explicit formula for these numbers. Nobody can. They're very hard to compute. However, I can relate it to some other equally unknown numbers, but not equally unknown, but certain things are known, and in part they are complementary to what is known here. And what I claim is that what we find here is a symmetric product space, and it's a symmetric product of what? So I'm sorry, I have to leave a little bit of space because there is a degree shift over here. Degree shift is, have to copy it, otherwise I get it wrong. It's n plus 1 according to my notes. And then what I have here is K is my ground field, which is always characteristic 0. So let's say Q for us. K, and this I have to shift by minus n minus 1. Then there's some product where J is equivalent to 2n plus 1 mod 4 and J greater or equal to 1. And then I have some element which lives where I have to shift by minus J.
A minimal model is covariant replacement, so derivations is just the space of generators of minimal model, right? So you are calculating cohomology of space of generators of minimal model, which are generators. What time is in? I mean, the derivation of free operads are. Oh no, you are not in. You are non-trivial values, I see.
I don't understand, but if you can compute it, I would be very happy. So I would be very happy to learn, because at least the right-hand side is very hard to compute. So if you compute the left-hand side, well, very good. And actually, both Drinfeld and Kontsevich tried to compute H1 of this. So if you can compute it, and they tried very hard. In fact, Kontsevich failed, and he created, because he couldn't do it, he created his formality theorem and this explicit solution. And Drinfeld failed, and he found this Knisnik-Samolotchikov associator and wrote his paper. So but anyway, so that's and then here's a complicated thing. So what is here is the graph complex. Which was defined by Maxim Kontsevich. But in contrast to, I mean, if you look at this, it looks formally very similar to the theorems that was on the board when Alexander Berglund gave his talk. But here, this graph complex is different from the one he talked about. So this is the commutative graph complex, not the Lie graph complex. And so this is as vector spaces at least.
You cannot see it from here. So J is comparable to n plus 1 modulo what?
Modulo 4. Yeah, it's a little bit, the board is too small for this formula. So maybe I put this part on the other board, if that's okay. And also I see that I probably forgot a shift here, and the shift should be 1 minus. So if k of minus n minus 1 plus k of minus j plus h of GCN. I will explain what this is in a moment. And I hope now all shifts are correct. And this holds as vector spaces. I'm not 100% sure about the Lie structure here, but what I'm sure about, I'm sure about the Lie structure of the primitive elements here. So the primitive elements are this copy here. So yeah, I will talk about this a little bit later. So there's a second part about the
Before you perform that last shift, is it an EN plus 2 algebra?
That's a good. Yeah, that's a question about the Lie algebra structure that I'm not. So conjecture, yes. But what I know is only that you see. I mean, here's a natural Lie algebra structure. So, I mean, the graph complex is a Lie algebra. This can be seen as part of the graph complex. So here, for J, this corresponds to, if you wish, to a graph that is a wheel with J spokes. Or another word is you have a stable cohomology of VLN, but maybe with degree shift. And on this part, there's a natural Lie algebra structure. There's a natural grading, and this guy acts as a grading generator. And then, if you compute any brackets of things within here, I know if you compute brackets of guys within here with some product, I think I can show that on cohomology, or I mean, on cohomology, that this is compatible with a product structure. But in general, if you compute the bracket of two arbitrary guys, I currently don't know. So I have my first graduate student starting in fall. I hope he can look at this. But currently it's not known, so it's only conjecture. If you can prove it, go ahead. So maybe just for completeness, let me give some remarks about the notation. So again, En is a chains operand on the little n cubes operand, and here, to be honest, I use some conventions that are not usually used. I kill the thing that is in arity 0. So usually the En operand contains something in arity 0 that corresponds to forgetting some boxes. But if you do that, if you keep that, then I mean the deformation theory is not so simple. In particular, to my knowledge, it's not known whether over Q the guy with the thing in degree 0 is formal or not. So Conservative proof shows that over R only, and you can lift the proof to Q using like minimal model theory, but I don't know whether it works in the other setting. And En, just for those of you who don't know, I mean, an operand generated by two operations. So the one is a product operation, so this has degree 0. And one is a bracket operation, this has degree 1 minus n, and the product and bracket have to be compatible. I mean, first of all, this has to be commutative product, this has to be a Lie 1 minus n bracket, and then they have to be compatible. I mean, in the obvious way that bracket with something is a derivation is product. And this whole En that I write there is just the minimal cofibrant resolution. So what I do is take the operatic cobar construction of the Kosyl dual, which is En Kosyl dual, and this is just the dual of the En operand shifted by n units. So this is the minimal thing you could possibly pick that is cofibrant. So why care, maybe? Let's say that so this object, so in particular this formality morphism, usually appears when you want to solve certain quantization problems. In that case, the left-hand side would be called the quantum side, and the right-hand side the classical side. And when you want to pass from one side to the other, in some way or another, you have to use a solution of this formality problem. We have like a diagram. Here we have en. Here we have lowercase en. So this is like quantum, and this is classical. And you want to pass from here to here in some form or of another. You need to construct such a guy. And this construction is very difficult. So there are currently no algebraic ways to construct this. So whenever you want to pass from here to here, you have to use transcendental methods, so integrals. And I mean, that's not proven to my knowledge, but it's like an experimental fact. Many clever people have tried and failed to construct an algebraic way to go from here to here. So, in particular, here in homological algebra, we try to use things by categorifying, whatever, doing all sorts of algebraic tricks. But if you want to go from here to here, there's no way. Can't do it. You have to. The only thing you can do is you can do some magic on this side to reduce it to this problem, and then you use the pre-existing solution of some way to go from here to here that internally will use transcendental methods in this construction. So in particular, one is interested in like how many choices do we have and should abstract it or not.
Discussion. What do you assume about your ground field?
Let's say we assume that it's Q. So the characteristic 0 at least.
Then you're saying that the coefficients, the weight conditions in the rational. The input
okay.
that you have to compute are not irrational.
Sorry, yeah. So the way, if you want different coefficients, then what you do is you start with a real solution, and then you change the real solution to a rational one. It's the same as you. I mean, in the case n equal to 2, the way from here to here is called a Grünfeld associator. And then if you want to construct a rational one, they exist, but you need to start from a real one, right? And the same for higher n. And again, if I don't assume this, then I don't even know. Then I have to say k is r. But I mean, for all I want to say, I think if we assume k is r, this will be fine. But I never will actually need it. So you can assume k to q.
Actually, I think that over R, the operator is formal even if you put a base point that is 0.
It is? Okay.
It's not known whether this descends to a cube from R. Okay.
Yes, that's what I said, right? Yeah. So yeah, yeah, over R. I mean, conservative proof works over R, but then. Yeah. And maybe one more definition, just to be clear. What do I mean by derivations of this operad? So I don't mean really derivations of the operad, but I mean a complex of derivations. And let's write it. So these are maps of S modules from P to P, which first I allow to have any degree, and I allow to not commute with the differentials on both sides that are probably there. But what I want to ask for is that if I compose two elements and then I apply F, that should be the same as Fa composed with the second element plus or minus depending on the degrees. A composed with F of B. So what if we have any degree and need not commute with the differential. If that is true, I can make a complex of such objects. There's a natural Lie bracket just by the commutator bracket, and there's a natural differential by the commutator with the differential I have on P. So let's write it df is equal to commutator of Lie with f. I hope it's not confusing. Or maybe delta f, I don't know. Use a different letter. It's very standard, and maybe I don't even have to write this down, but there's one little bit non-standard convention that I want to remark on. So, in particular, let's say P is of the form we consider, so it's bar construction of some cobar construction of some cooperate. Then let's denote it by Twiddle for the moment. Twiddle of P, it can be identified because this is free or quasi-free with some product. And for simplicity, let me also assume that P has no operations in degree 0, and in degree 1 you have only one operation, so, and C has to be co-augmented, but we only apply this to En, and there everything is satisfied. So then you have equivariant homomorphisms from En, there's a degree shift, -1, I hope, into Pn. And so this would be the standard definition of the derivations. Now, my little bit non-standard derivation is to, or my non-standard definition is to start with n equal to 1 here instead of n equal to 2, which would correspond to allowing f not to respect the unit here. Not necessarily annihilates the unit. This has the advantage that from the answer from this cohomology we actually remove one class, and this one class corresponds to an automorphism that is there for any operad, which is just by rescaling by arity. Right? If you have any operad P, there's an automorphism which on Pn acts by multiplication with lambda to the n-1. This is kind of trivial, and that we want to kill. And this non-standard convention here does that, but of course only relevant if you happen to find some class in your computations that I don't have in here, maybe this one. Another thing we should be aware of, I mean, I want to make everything very explicit. So, what is the En operad? So I gave you generators and relations, but how does En in particular look like? So you can notice that this has a basis of, let's call them N Poisson words, which are some formal wedge products of Lie words and some variables x1 to xn. So here you have some Lie words, and they are, you take a formal commutative product of them, and each xj occurs exactly once. Now, I'm sorry, I think I bore some people with this discussion. I will cut it short. But what I want to say in particular is if you have the En star operator, you look at En star n, it's something similar, but here you have formal co-products of co-words, and these you can think of as associative words modulo shuffles. So that you should, that's the only non-trivial or points that maybe the younger people don't have in mind, that the dual space to this Lie operatus is obtained by the associative operad if you mod out the shuffle words. So this means modulo shuffles. So if I insert everything in this formula, what I get is a rather explicit expression. I can make it a little bit simpler already. Namely, there's also the notion of a derivation of an operad map. So, say we have an operad map, let's call it capital F from P to Q. Then, let me change the definition here. We have a map of S modules from P to Q. And this is a derivation if the map identity plus, or let's make a concrete sentence. So F is the derivation of degree K if the map 1 plus epsilon F is an operad map from P tensor K of epsilon over epsilon square into Q tensor K of epsilon over epsilon square. Actually, you don't need even this one. Don't even need that. So, if that is an operad map, we say that F, sorry, I forgot one thing. Epsilon is a formal variable of degree minus K, and if that is an operad map, we say that F is a derivation of degree K.
Is that one capital F or?
I'm sorry, yes. Was already in, still in the last case where specialized is just one. And then in our original definition maybe obtained by replacing F by the identity map. That's just a remark, and if we have operad map from P to Q, we have a similar formula. If our operad P has this form here. Here I'm again using somewhat obscure notations. I denote this by def, and I omit this degree shift here. The reason is that this forms also a DG Lie algebra, which is a kind of convolution DG Lie algebra. But the Lie bracket is something different than the Lie bracket we have here. So on this space, actually, two Lie brackets of different degrees. They're not the same. And I want to use this notation to clearly distinguish. So here there's a Lie bracket by composition. Here we don't have a Lie bracket by composition. There's another one, but this we don't care so much. And then one thing to check is that the first thing we have der P is isomorphic to deformations of the identity map when I shift by 1. And another thing to note is that if P to Q is a quasi-isomorphism, then I can compose it at the right and get a quasi-isomorphism of the deformation complexes. So this is quasi-isomorphic to def PQ if Fp to Q is a quasi-isomorphism. So in particular, the obvious candidate for Q here is the operad En itself, right? So I can, in our case, so the goal is to compute def for En to En, right? So I can compute that. I have, at least as a vector space, I have computed my right-hand side in the theorem. But of course, this does not have the correct D-algebra structure. That's why I make this distinction. Right? That's something to be kept in mind. So okay, I spent like 20 minutes to explain something that's probably obvious to most people. So let's talk about the right-hand side. So the right-hand side is quite interesting. So in particular, we want to understand this graph complex. So let me say what it is. Let me define it in a slightly operatic way, since it is a conference on operads. Let me first define the set of graphs. So let me say what I mean by a graph. Again, this is maybe obvious to most people. Let's call it graph nk. It's a graph with n vertices and k edges. Set of directed graphs with vertex set n and edge set k. So what does it mean? These are just k pairs of numbers. So such a graph is consists of k pairs of numbers I1, J1 up to Ik, Jk that tell you from where the edge goes to. And that seems very obvious, but it's important to be really precise, because often in papers, including my own, notions of graph and automorphism class of graphs are confused, and then it can get really confusing with time.
So you assume enumeration of vertices part of the structure?
Yes, so the numbers on the vertices and the numbers on the edges and the directions of the edges are all part of the structure. And then I define an operad that I call gra n. So if I look at the n-ary operation, so the small n is globally constant, not just on connected components, so it's the same as En. And this capital N is a number of the arity. And this is what? This is, again, there are degree shifts, so I have to get my sheet, otherwise I get some more. So these are a k-linear series in elements of gra nk, so arbitrary formal linear combinations, possibly infinite, of elements in here. Then you tensor with some copies of k shifted in degree n minus 1. You take as many as there are edges, so the edge has degree 1 minus n. And finally, you mod out by s2 to the k, mod out by sk, semi-direct product with s2 to the k, where the action of the symmetric group in k elements is by permuting the order of the edges. The action of the symmetric group in two elements is by flipping the direction of the edges. And sk acts also here, possibly with the sign by interchanging the factors, and S2 acts by sign if n is odd and not by sign otherwise. This is some complex, so here might be not so obvious why would I have defined these things. It will become apparent in a moment.
S2 acts by sign if who is odd? K.
Oh, I'm sorry. This is of course wrong. N is odd. Thank you.
Sorry.
I forgot. Sorry, I forgot. Yeah, here I should have the union of all k. So I take a product over all k. So there can be graphs with arbitrary many vertices, and for each I kind of forgets the labeling, forgets the direction. So at the end we have isomorphism classes of undirected graphs with unlabeled edges. But of course there are some sign issues, and I always get the question, what about the signs? Usually, what I usually do is I just write a sloppy definition, modulo signs, but then people are usually not happy with that. So this is a precise definition. This guy is an operad, I claim. And well, let me give an example. Maybe an example explains better why this is an operad. Let's say I have this graph here, and let's say I want to insert into the third, into the vertex labeled by 3. I want to insert this graph over here. And what I do is I erase that vertex, put in that graph, and reconnect all edges in all possible ways. So in that case, that would be, first of all, both could go here. Second of all, both could go here. Third, one could go here. And finally, one could go here, one could go here. And there are some numbers, 1, 2, 3, 4, 1, 2, 3, 4. They're all the same. And this procedure, I never know how to write it out formally, but I mean, combinatorially, it should be clear what the procedure is. And then we can define a graph complex. So, I mean, whenever we have an operad, then the space of invariant elements, invariant under the symmetric group actions, is a DG algebra. That's a general fact, and the DG algebra we get out from here. That is one version of the graph complex. So I write it out in a little bit more fancy way. So FGCN is, let me note one thing. Note, I mean, the signs there were defined such that there is a map from the n operad into gra n that sends the product to the empty graph, and the bracket to the graph is one edge. And then you can take the space of invariant elements, and you can check that will be the same as the deformation complex of the map from the Lie part from here into here. So I call that, let's say, wholly n into gra n, and this is just the same, of course, as the space of invariance up to some degree shifts. But from this description, it's clear that it is a differential graded Lie algebra. So there's a Lie bracket. Yeah. Something important that certainly was known to Kontsevich when he wrote down his complex, but it's not, I realized, known even to people working on graph cohomology generally. So
it's absolutely impossible to see the degree shift from here. It's around the corner.
You mean I can always say afterwards that it was on this board? The degree shift here is, so the vertices should have degree little n. That's what the degree shift is. So it's n minus n, I think. So it seems I will not be finishing early today. And then what we can define as a graph complex, that's sorry. What we define there is the full graph complex. That's why I called it FGCN. And then Kontsevich had a kind of simpler definition, or defined a smaller complex actually, which he called GCN, which is a sub-DGD algebra in FGCN, which consists of graphs that are connected and where all vertices have degree at least 3. So it's a subcomplex, and furthermore you can express the cohomology of this guy in terms of the cohomology of this guy plus some known classes. So all the complication in computing the cohomology of this is contained in here. So in general, then one can ask, what is the cohomology of GCN, at least if one is interested in this theorem, and the answer is nobody knows, but there are a couple of classes which are known to be non-trivial. In particular, I can draw the following picture. Well, before I draw a picture, so actually what I would have to draw is draw a picture for every n, right? But fortunately, there's a kind of twofold periodicity. So it only matters whether n is even or odd. And if you just look at the definitions, you see these were undirected graphs modulo some signs. And if I shift n by 2 units, then the signs all stay the same. It's just that certain graphs now live in different degrees. So let's write this up to degree shift. GCN plus 2 are the same. However, GCN and GCN plus 1 are, at least from what it looks like, quite dissimilar. So let me illustrate this, and let me draw some picture about the cohomology of these graph complexes. So let's only talk about one even and one odd case, and we have understood everything up to some shifts. Let me make the following diagram. So there's natural bigrading. The bigrading is, for example, by the number of vertices and by the cohomological degree. Right, that we can write down. And let me draw something. 7, 8, 9, 10, maybe 11, 12. And part of, so I will I'm going to write down a picture of the cohomology, so numbers. I'm writing down an array of numbers. And the way to obtain these numbers is as follows. So part of the information comes from the left-hand side, part of the information comes from the right-hand side, and part of the information is from computer experiments. Okay? So what comes from the left-hand side? From the left-hand side, what we can learn is that the cohomology is 0 in negative degrees. And if I'm in degree 0, what we see there is a Grothendieck-Teich-Müller Lie algebra. So this was first shown by Tamarkin. So the Grothendieck-Teich-Müller Lie algebra injects, and then I could strengthen this to showing that it also surjects. So here the dimensions are as follows. So you have 0 for 3 vertices, 1, 4, 0 for 5, 1 for 6, 0 for 7. Then 1 for 8 and 1 for 9. So this would correspond to sigma 3 if you know what the Grothendieck-Teich-Müller Lie algebra is. This to sigma 5. And then I have a bracket of sigma 3 and sigma 5. So it's there. That's why there's this 1. Here there's another 1. And I think for 12 vertices there's the first 2. Then if I look in degree 1, these are all zeros. If I look as far as the computer could check, actually the conjecture that in degree 1 you get 0 is very hard. So this was essentially tried by Kontsevich and Drinfeld. Cannot doesn't prove it. Then in degree 2 the computer says that it's also 0. In degree 3 there's the first classes above that are non-zero. So the first one, so here they're all zeros, 0, 0. And the first one has 10 vertices. And then there's another one with 12 vertices. Here these elements are 0. And then there's the next, here we have GRT. I don't write the numbers, but the next element that is non-trivial has 18 vertices and lives in degree 7, I think, somewhere over here. And what you can easily check is by just using the constraints that you have only trivalent vertices, that the whole cohomology must live in some wedge. So there's a line here above that it's 0, below that it's 0, and the cohomology is concentrated in this wedge. And what you should notice is that on the lower rim of that wedge we understand it very well. The numbers grow relatively fast, so there are many classes here. So and above that we have more or less sporadic classes, but we don't even have a conjecture or theory how these classes should be distributed. But these numbers here are not very large. Of course, maybe somewhere over here they suddenly start to rise. I don't know. And let me also say some names. So the injection of GRT into here was proven by Dima Tamarkin, and I could show that actually this is isomorphism. And computer experiments, I wrote a computer program. I was quite proud, but little after I learned that 20 years ago computer experiments have already been done by Barnatan and McKay. Of course, at least they had the advantage of 20 years exponential increase in computing power. But so let's Barnatan and McKay. That's how the picture looks like. Then if I go to other n which are even, this wedge will be moved downstairs. So kind of will be skewed downstairs, but the numbers all stay the same. So this is a picture for all n. Let's look at odd n. Again, we plot the degree versus number of vertices. And what you can easily find is that again, just by counting the number of edges and vertices that you can have, the first non-trivial classes can possibly appear in degree -3. And the classes that appear in degree -3 are very well known in knot theory, and they compute some finite type invariance. So you can use them to construct invariance of 3 manifolds, or at least of rational homology spheres. More generally, you can use these graphs to construct classes in the classifying space of the diffeomorphism group of manifolds of odd dimension. But these numbers are very well studied. So, for example, the first one, I have a class with 2 vertices in degree -3. That would correspond to this well-known zeta graph. Maybe if we call it zeta graph, you have to write it the other. You have to draw it like this. And then the next one is with 4 vertices. So this is the tetrahedron graph, and then it goes on. So in 2, 4, 6 it is 1, 7 it is 0, 8 it is 2. I mean, every second one it is 0. You can easily count that. 10 it is 2. 11 it is 0. 12 it is 3. Then it is 0. Then it is 4. And then it goes on. If you go to, again, by similar arguments as you did here, you can find a lower boundary for the cohomology, so it's 0 somewhere below here, and everything is concentrated in a wedge. And let me just write down these numbers that I don't understand very well. So the first is 7 minus 6. There's a 1 here, and a 0 here. There's a 1 here. Everywhere here it's 0, and somewhere below this line we don't know. So these are the classes that are known. And I'm sorry for filling the blackboard and my time with numbers, but there's one thing I want to remark. Or I want to request somebody to teach me something. Namely, often I heard these words that the deformation theory of CEN and CEN plus 1 operad is essentially the same. But or it's the same up to degree shift. If I look at these 2 tables of numbers, the simple-minded person, I would say they are not the same, right? And they are not obtained by any simple permutation. Also, there's another statement that GRT would act also in the odd case that I don't understand. I mean, here we find GRT, and it corresponds to graphs. For example, the sigma 3 corresponds to this graph. Sigma 5 corresponds to this graph here. This is sigma 3 in GRT. This is sigma 5. 5 over 2. And if you want to find analogous elements in here, you have to ask, where do they live? How do I obtain these graphs? And if you look at this, then, well, you can say, oh, there's an obvious map. You just interpret the graph as the same graph, but maybe with some different sign. But you see, the signs do matter in this case. For example, if I want to do it here, and I just interpret this graph as an element in the other complex, that will be 0. Because there's a symmetry. If you flip left and right hand side, there's an odd symmetry which will make this guy 0, and similarly there's an odd symmetry which will make this guy 0. So I can't say they're not the same, right? They're infinite dimensional spaces. Maybe something is going on, but if they are the same, if you can relate, yeah. Yes, but yeah, I'm talking about the statement that En and En plus 1 have the same. Of course, if you if you have the same parity, then it's the same. Yeah. But you have periodicity 2, not periodicity 1. That's what I'm saying here. Unless something really fantastic is going on. So I have 4 minutes to discuss a proof.
The zero line on the for odd case is known, or what is conjecture mean?
Which line?
It's the -3 line.
This line is also not known.
No,
it's
the
conjecture.
first line.
This is
No, where you have 1, 0, 1, 1.
No, it's not.
The first line in the odd case. In the odd case.
-3, like the one that actually.
It's -3 line. Yeah.
no. This is. I mean, this is by computer experiments. These numbers have been very well studied. There are a lot of classes, but to my knowledge, there's no explicit formula for what the numbers should be. So, I mean,
Even the conjecture, like in GRT, there's no.
no, there is not even a conjecture how to get these numbers to all degrees, as far as I know.
Okay.
But of course, there are a couple of ways to construct elements. So every quadratic Lie algebra gives you an infinite series. So you have, and these classes that you obtain are automatically non-trivial. So of course you can, if they are non-zero. So, but of course it doesn't answer the question of how many there are, right? So, and that is, to my knowledge, not.
Related to the computation by Turchin, when he computes the Hochschild homology of the Ian open. And it reminds me of this story because there is an odd and even answer. And so somehow he has some, some estimate on the how many generators you get. So he has some kind of estimate. But I don't know.
Of Concevich's computation?
Turchin.
Turchin? I don't.
I mean, he also did computer computation because it's related to London knots.
Okay, yeah, I don't know that.
And this could also be related. Okay, maybe it should.
Yeah, there's.
Very similar.
So I have 1 minute to discuss the proof now.
5 minutes.
5 minutes?
On that.
Okay. Maybe you can just turn all around. Is that okay?
Yeah.
It's recorded. Oh no. So, may I give you the first step of the proof? So let us recall how Koncevich proved the formality of the n operad over R at least. So what he constructs is a certain operad of graphs, and in contrast to my operad graph we had before, this operad will have two kinds of vertices, some numbered vertices and some unidentifiable vertices. So it can be obtained formally from this operad graph by adding one additional generator which is zero array. So that would be where the zero array guys go, and then considering only those parts where each connected component contains at least one external vertex, and throwing out a certain graph. And there will be a natural map from graphs n to gra n, and it's not hard to see that the map from En to gra n factors to graphs n. There's also a differential here, so a differential acts on internal vertices by splitting them, and on external vertices also by splitting them. I just write these pictures. And what Koncevich showed, and also Pascal Lambrechts and Isma Volic, that the map from here to here is actually a quasi-isomorphism. And then what he says is that to the corresponding dual or pre-dual operad, there's a natural way to assign to every element, so to every graph, a differential form on the configuration space of points in Rn. And the way to assign a differential form to a graph is that for every vertex you assign some point in your configuration space. To every edge you assign a differential form, which is just a pullback of the volume form on an n-1 disk. And a forgetting of all the others and forgetting of scale. And then you integrate out over the anonymous vertices, over the internal guys. And this gives you a differential form. And when you have a differential form, you can integrate it over chains to get a number. And then if you sum over all graphs with those numbers, then this gives you a map from the chains in this operad introduced by Getson and Jones originally of right, it's Jones operad of configurations of points in Rn, and this is a quasi-isomorphism, and here is some technical point I ignore. And now the main statement, or the main thing you have to check, is that combinatorially you have an action of GCN on this graph. And if you have an action of GCN on graphs n, then what you can do is we can work in the deformation context not from HOEN to En, but from HOEN to graphs n, and having an action here gives you a map from GCN into this complex over here. And the image will essentially be the primitive things here. And then if you look at this guy, it naturally decomposes into the product of connected components. And if you compute each connected component, you see that actually this map is a quasi-isomorphism. That's in short the proof.
By action, do you mean left action or right action?
I mean, you can go from one to the other, but it's a left action by operatic derivations. So it's I mean, there's a.
Which guys are you inserting in which? Do you insert the graphs in the GC graphs or the other way around?
Both. You have to do both.
You do that. Okay.
So there are a couple of terms. You have to plug one in the other, and then minus plug the other into. We can discuss it if you want. Yeah.
Further questions? Okay, so